In this video, we present our paper CASAPose, Class Adaptive and Semantic-Aware Multi-Object Pose Estimation. My name is Niklas Gard, I work at Fraunhofer HHI and I've written this paper together with my colleagues Anna Hilsmann and Peter Eisert. Our task is to estimate the 6D poses, the positions and orientations of known 3D shapes with respect to a monocular camera, to establish a correct matching between 3D model and image content. Poses are required for tasks in augmented reality and robotic object manipulation, where often also real-time processing is needed. Also, many applications require to estimate poses of multiple objects simultaneously in an efficient way. Here, state-of-the-art methods still have some drawbacks. A common approach is to train one CNN per object, which means that multiple network inferences per image are necessary and that every model only has limited knowledge. Often, especially in presence of a synthetic-to-real domain gap, an additional 2D detector is inserted into the pipeline, making the methods two-stage, adding even one more CNN as well as intermediate processing. An alternative is to branch the output in the last network layer and to add extra output maps with every added object. Since usually multiple outputs per object are needed, the output space becomes large, which makes the models difficult to train and introduces performance issues. Our approach uses a separate decoder only to estimate the semantic object masks and feeds them to a semantically guided decoder as side input. The second decoder does not have to split the output per objects and instead provides information for all objects in a combined output. This results in simple end-to-end training and fast inference in multi-object applications. In addition, our method is optimized for use with synthetic training data, and local feature processing minimizes the domain gap. Similar to the well-known PVNet, our method predicts unit vectors towards 2D locations of predefined 3D keypoints on the object surface. It calculates common intersection points and estimates the pose from 2D 3D correspondences. Like them, we use a lightweight ResNet 18 backbone, but then instead of splitting the output with the aforementioned disadvantages, we carry out a few design modifications. First, an additional decoder is added, which avoids splitting the vector fields of the key points per object, but instead merges them together in a combined output. Next, the segmentation is fed into the decoder modules and is used in segmentation-aware and class-adaptive operations, which we will introduce on the following slides. Last, the semantically guided decoder also learns to predict confidences for the estimated vectors, which are used directly to calculate the 2D keypoint locations within the masks with weighted least squares. Class adaptiveness is added to the network by inserting object or class-specific weights. We make use of the idea of conditional instance normalization for that. Here, the output of a convolutional layer is first normalized and then denormalized with a learnable affine transformation. The choice of the denormalization parameters depends on the predefined input class. In our case, the input class is the class of the observed object. To know the class of the observed object directly in the training, we use the semantic mask to select the corresponding set of parameters dynamically depending on the spatial location in the latent feature array. The operation is called class adaptive denormalization, or CLADE. Depending on the position, a different row of a learnable matrix is copied into a dense modulation tensor. This is then multiplied with or added to the normalized input features. Semantic guidance is further achieved through two more guided operations in the decoder. The idea is to improve the alignment between the estimated mask and the latent features. This ensures that CLADE only affects features within the mask. A guided convolution evaluates the semantic mask at the filter position and then only considers features from the same region. A naive upsampling would now lose the alignment with the next higher resolution mask again. Instead, a guided upsampling helps to upscale the features between the high and the low resolution semantic mask without losing that alignment. The effect of semantic guidance can best be seen in direct visual comparison. The baseline method using a single decoder produces artifacts at the object boundaries. In contrast, the semantically guided decoder outputs clearly separated vector fields. The ability to separate the individual regions positively impacts the pose estimation. The last modification is the integration of a differentiable keypoint regression, which replaces the otherwise frequently used non-differentiable Runsack-based keypoint estimation. A single keypoint is calculated from all vectors of a region using a weighted least squares method that minimizes the sum of squared distances with respect to a cost function d. A learned confidence weights the pixel-wise equations. The loss function directly evaluates the result of the equation system and optimizes both the calculated 2D position but also vector accuracy and confidences. Since the operation is formulated as a network layer, the network can output the 2D keypoint positions directly and calculate them in parallel. Here we see that the estimated confidences are dependent on the location of the keypoint to be estimated. If it is in the center of the object, all pixels can contribute equally to the calculation. If the keypoint is at the boundary of the object, we observe a focus on the object contour or on the nearby region, especially the access to the object silhouette over the guided convolutions with the semantic masks helps evaluating the keypoint locations as precise as possible. The contour is a domain-invariant feature which has a positive effect when training with synthetic data. We will now discuss our experiments. During training, we only use synthetic data, and because of the effort involved in capturing and annotating real data for multi-object scenes, we think this is the only practical way to train a multi-object model. We use the physically based rendering PBR images of the Bob challenge and test on the standard LINEMOD and Occluded-LINEMOD datasets as well as on a subset of HomebrewedDB. LINEMOD contains 13 objects that can be found in all 3 datasets. For the evaluation, we measure the average distance metric ADD and the projection 2D metric. In the following, we report the ADD metric. In this context, a higher value is always better. The Ablation study measures the influence of our core design choices on 3 datasets. Adding the split decoder and the class adaptive denormalization improves the result for real as well as for synthetic test data. If the semantic-aware convolution and upsampling operations are included, this increases the accuracy even more. The differentiable keypoint regression already improves the baseline model by a large margin, as inaccuracies are filtered out through the confidence maps. It is remarkable that the semantic awareness through access to the silhouette improves the result for the real data more than for the synthetic data, which confirms our previous assumption of increased domain invariance. We evaluate our approach with respect to the network capacity, the number of objects one network can recognize. On an 8-object subset of LINEMOD, we observed similar performance for an 8 and 13-object model, indicating a closure of the multi-object gap. Still, on the more challenging LINEMOD occlusion dataset, the 8-object model outperforms the 13-object model. If we further reduce the capacity and train 2 models for 4 objects each, the accuracy increases further. This can be partially explained by the exclusion of symmetric objects from one object set, which improves the convergence for our correspondence-based method. We compare the performance of CASAPose on the challenging LINEMOD occlusion dataset to several state-of-the-art approaches which also train on synthetic data. The table shows that our results are superior to another single-stage multi-object approach, to several recent semi-supervised methods which also include unlabeled real-world data during training, and to another recent multi-stage method. We also compare CASAPose to the well-known single-stage multi-object approach EPOS using the metric from previous Bob challenges. The accuracy of our method is similar, but our method is multiple times faster. One sequence of the HomebrewedDB dataset is frequently used as benchmark to evaluate domain generalization of a method, since it shows 3 LINEMOD objects captured with a different sensor in a new environment. We applied the 13-object model without retraining and surpassed the next best method, DAKDN, by 35%. The good result can be attributed to our method's enhanced ability to bridge the domain gap. In addition, correspondence-based methods tend to be more robust towards camera changes. To conclude, CASAPose achieves state-of-the-art results with synthetic training and only one network for multiple objects. The reasons for that are that class adaptiveness and semantic awareness improve the performance of a multi-object 6D pose estimator, that local feature processing minimizes interference between overlapping regions in a reduced output space, and also that differentiable keypoint regression reduces the domain gap, especially in combination with semantic-aware operations. A next step in future work could be to make the method instance-aware to allow multiple instances of the same object by applying the introduced guided operations directly on instance masks. Our custom layers can be integrated also in other pose estimation architectures and potentially also bring benefits there. Therefore, we make our training and testing code available on GitHub. Thank you very much for your attention. If you have questions regarding the paper, you can contact me directly via email or at the poster presentation at the BMVC conference, or write your questions directly into the discussion box on this website.